Okay. What is the chat? Okay. So consider the gravitational field. F, and that was given in a previous example. Defined on, now let me just avoid the this is just an easy example. Let me just avoid the center 0, 0, 0 because it's where the gravitational field will blow up. So we're gonna consider a sphere that is a bit away from this, the, okay? So when you have an inequality, it means that it's the inside and also the surface. So remember, what was the gravitational field? It's minus these are constants, x squared plus y squared plus z squared, okay, plus minus g y x squared plus y squared plus z squared 3/3 g plus minus capital M g z x squared plus y squared plus z squared, okay? So you need to compute the curl of f. So the curl of f. Now I'm not gonna do it on all the details, but for example, for instance, if you take the derivative with respect to y, of this function, if you take the derivative with respect to y of this function z, x squared plus y squared plus z squared 3/2, this will be exactly equal to the derivative with respect to z of the function y over x squared plus y squared plus z squared over 3/2. And they will be both equal to minus 3 y z x squared plus y squared plus z squared minus 5/2. Okay? Okay? So if you compute the curl, you're gonna get a lot of this kind of derivative with respect to y. Just use the formula of the curl. Remember, what is the formula? You have to take the curl of f. You have to take I, j, k, take the derivative with respect to x, derivative with respect to y, derivative with respect to z, right? And take the fx component, take the fy component, take the fz component, and then compute this. Apply this here, apply this. So what I did here, right? What I did here is just this one, right? So I applied dy on fz and I applied dz on fy, okay? I didn't want to include the constants m, and g because they're just constants. So when you do it for the other components, it's going to give you the same thing. So when you, it'll actually be 0. So because this sphere is, because f is defined on this sphere, right? The sphere, remember, the sphere is a bit away from the origin because here we're divided over x squared plus y squared plus z squared. So you can, if you define it all, it's not defined on all R3, right? So it's gonna be a bit problematic if you wanna apply the theorem for this case. But in this case, a sphere is simply connected and you apply it so it's conservative on the sphere, right? Because remember, I mean, a vector field can also be defined on just a sphere. It's possible. But in all the cases you're gonna see. So here is a homework I'm gonna give you. And this is very important. So it's got a kind of bonus of attending the class. So in the quiz for this week, okay? The quiz for this week, there will be a lot of conceptual questions. You're gonna see some kind of questions like, is this vector field conservative? Is it path independent? Is it these kind of things, right? So what I would highly suggest is go back to the theorems, like those theorems that we've seen in the 2D case, and they are the same in the 3D case, and review them. Make sure you understand them, make sure you how to apply them, okay? Another thing is, so this one is important to make sure you have a, mark it down somewhere. So go to, so there is an exercise I would like you to do, which is not hard, but I would like you to do. So I'm talking about this kind of theorems. We did it, right? If the curl of a gradient is 0, the curl of something like, is it possible to have, show like these kind of questions, show that the vector field is not conservative, show that, you know, these kind of questions. Okay. So I would like you to do this homework here. Where is it? Mhm. Where is it? Let me see. It's not surface areas, of course. But why is it? Yeah. So you remember in the 2D case, we had the analog of if a vector field is conservative, right? If it comes from the gradient of a function, then we used a Clairaut theorem to prove that dy of p is equal to dy phi. In 2D case, go back to the 2D case and remember we had only one equation. For if it's conservative, then this must be true. And they have continuous first order partial derivatives. Then we had only one equation, right? Now I would like you to do the exact same thing. It's not hard. I would like you to do this exercise here. 29, okay? And apply the same exact reasoning as we did in the 2D case and apply the Clairaut theorems 3 times, and it's gonna give you this, okay? And then I would like you to keep this exercise in mind when you are solving the quiz, okay? this week, tomorrow, okay? So you're gonna use this, you're gonna need this, okay? So I'm not gonna say more. Okay. All right. All right, so this is pretty much all we need to know about curls. Divergence of vector field. Okay, so this is the new concept of three-dimensional fields. Let F be a vector field. Okay, on R3. And suppose, give me one moment. Yeah, sorry, that was an emergency. Okay, so, and suppose that del X, del Y, Q, del Z, R exists. Okay, then it's a pretty much easy formula. Does useless? It's useless in the sense that it's only just to, I mean, it doesn't matter, to be honest. I mean, you can define it everywhere. I mean, I just wanted to define it somewhere where we don't have the origin, right? You can define it on any region outside the origin. It's really useless. It has nothing to do, right? But of course, it's not going to be useless if we're going to do some kind of, we're going to see that if you want to compute, for example, the surface integral over the surface area, then it, of course, it's going to depend on if it's a sphere, or if it's a paraboloid, or if it's an ellipsoid, you know, it's going to depend on the surface itself. But if I just tell you, okay, this is vector field defined on the sphere, yeah, fx, fy are the components. So this is fx. Sorry, thank you for reminding me. So this is fy, and this is fz. Okay, so this is the formula for the curl. Okay. Does it make sense? Right? So this is just an example. It has nothing to do. Okay, so the formula for the divergence it's really the same thing as for a curl. It's just a formula you have to apply. It's you take d dx d pi plus dy dq plus dz dr. Okay, so formally speaking, so also make sure you understand these notations. Formally speaking, this is the scalar product of the gradient with the vector f, right? So this is kind of formal, this is symbolic computations. It's dx, dy, dz, scalar with p, q, and r, right? Okay, so for example, compute, for example, the divergence. So if f is equal to x I plus y j plus zk, then the divergence of f is equal to the gradient of f, gradient times f, which is equal to dx x dy y plus dz z, which is 1 plus 1 plus 1, which is 3. So it's a number. So the curl, okay? So when P, Q, R have continuous second order partial derivative, we get the divergence of the curl of f is equal to, well, what is this? This is the gradient times curl of f. So make sure you understand these notations here. This is 0. So this is a vector, and this is a number, is a scalar. A scalar. Okay. So why is that true? I mean, this is really a computation. So indeed, you have to compute this here. So what is, so by definition, what is this? This is Vx of the x component of this vector here. And if you go back to the definitions, this is dy, dr, dy minus dz q plus dy dz p minus dx r plus dz dq minus dy dp. Okay, so there will be a lot of this kind of equalities that you have to show in the problem list, and it's all done in the same way. You'll have to apply the definitions and manipulate all of these equations, and then you're gonna get something. So, for example, this is d squared dx dyr minus d squared dx dz q plus d squared dy e minus d squared dy dx r plus d squared dz dx r q minus d squared dz dy Okay. So the reason why we ask them to be continuous second order derivative is because we can then use Clairaut theorems to conclude that this is exactly the same as this. The order doesn't matter. So this goes with this because of Clairaut theorems, and this one, sorry, this one is d squared dz. Okay, and this one will go with this one, and this one goes with this one. Okay, because since okay, because by Clairaut theorems. I hope this is the right way to spell it. Okay. 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 Take f x y z to be a function that is equal to x squared plus y squared plus z squared. Okay. So what is this? Now, sometimes it doesn't make sense. Make sure that you understand. Okay. So this is a vector, and so what is this? This is the divergence of the vector field gradient of f, which is equal to divergence of, so what is this? This is 2x I 2y j plus 2z k. And what is the divergence of this one is dx 2x plus dy 2y plus dz 2z. So the divergence is a bit easier than the curl. So this is 2 plus 2 plus 2, which is 6. Okay. So divergence, so it's not a dot product. Which one? Which one are you talking about? This one is not a dot product. This one is not a dot product. The divergence is a dot product. Dot product is exactly as a scalar product. So it's really a dot product. Right? So what is the definition of a dot product? Look, go back here. What is the definition of a, if I give you two vectors and I ask you to compute the dot product, is you take you multiply the first component by the first component plus the second component times the second component time. So this is a symbolic way. This is not a vector. This is an operator. Dx, dy, dz. It's not a vector. It doesn't make sense. It's dx, dy, dz here, right? This is not a vector as a usual vector. This is a vector. Right? Evaluated at some point, it gives a vector, but this is not a vector, a usual vector. It's an operator vector. But as a symbolic way, a way to remember, it's you take the dot product of this thing times the, it's the same thing as we did with the curl. We took this vector here and we just saw it as a vector, right? Just make sure you multiply on the left. What's the symbolic vector? Yeah, so a symbolic vector is this one. It's dx, dy, dz. This is what I call a symbolic vector, right? This is the first component is d del the partial derivative with respect to x. The second component is the partial derivative with respect to y. So, because it doesn't, I mean, just like the partial derivative with respect to x, it needs a meaning of what, which function, right? So if it's just like this, it doesn't have a meaning. But as a symbolic way, we just do it like that. And this might be a little bit strange in the beginning, but it works. If you take the scalar product of this as a symbolic thing, you take the scalar product with this one, it works. It gives you exactly this. You multiply this by this, but of course the multiplication is not the usual multiplication. It's apply d when you write dx del the partial derivative with respect to x. Now this is not a multiplication. It's not a normal multiplication. It's apply this to the function p. Yeah. Okay. So this is how it how it is done. Does it make sense? Does it make sense? Okay, thank you. All right. So yeah, so this is pretty much all we need to know about the divergence. It's computations. But of course, this is just ingredients we're gonna need for Stokes theorem and divergence theorems. All right, so now I'm gonna introduce a new section, which is parametric surfaces and their areas. Okay, so remember what is a curve on a space. A curve in a space is if you are in 3D, right? And you have a curve in the space, okay? So this curve is what is the parameterization of this curve? It's only one variable. It needs only one variable. It's some function xu plus some function yu plus some function zu k. Okay. Now, if you have a surface on the space, you'll need two variables. Okay. The surface in R3 is given by the parametric equation is given by the parametric equation. So you will need two variables, u and v. And of course, you will have a function of two variables here. J plus z uv k. Okay? So this is a function in 3D. And u, v are inside some domain d in the UV plane. Okay? Example. Consider the parametric, because remember here, you already know a certain form of expressing a surface in 3D space. You remember this is what I've been doing since the beginning. It says z is equal to fxy, right? It's the surface given by the function fxy, but this is very restrictive. There are some surfaces that you cannot express as a for example, the easiest one is a circle. A circle you cannot express as a, this is just a curve, right? This is just a curve, but you cannot really express it as a function of y is a function of fx. You cannot express a circle as a function of fx, right? You can express half circle as a function of fx. You can do that. Half circle, you can do that. You can do that for a half circle, but for a whole circle, you cannot have a function. So you will need a parametric representation of the circle if you want to have it like in one. If you want to have one like a circle, the whole circle, you'll need a parametric representation. So the same thing applies for surfaces. You can have a sphere, for example. The sphere, you cannot have a function that gives you z is equal to ta 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 ta, and this is the sphere. No, it's never possible. You can have half the sphere, can have a hemisphere, but not the whole surface. So that's why parametric surface representations, we need them, because there are some surfaces that you cannot really express them as you know. So for the one who needs me to scroll up, is this okay? So take the vector uv as well. Here it's in terms of as a. Of course, uv doesn't mean nothing. You can have st, and this is you're gonna need. You're gonna need to start forgetting about uv. You will need sometimes z. You need sometimes x. You will see what I'm talking about. But keep in mind, you have to keep in mind the meaning of all of that, not UV. UV is just a variables. You can have xt, you can have st. So for example, here I'm gonna use the variables st. And here it's s cos t I plus s sine t j plus s k, okay? So what is this surface? And here you need also you always need to express the 2 pi and s between 0 and 1. Okay, so what is this? What is this surface? So here we have, so this is x, st, this is y, st, and this is z, st. We have x, st is equal to s cos t. We have y, st is equal to s sine t. You have z, st is equal to s, okay? We meaning that if we take x squared plus y squared, it gives s squared. Okay? Which means this is also equal to z squared, which means that z, because z is positive, Okay, so can you remember what is this surface? So this is the surface. You have seen this a couple of times when computing double integrals and triple integrals. That's a cone, right? That's a cone. That's the cone. This is the surface. Corresponds to a portion of a cone. Okay? So this is what you've been used to, z square of x, but this is another representation of the cone. See? Now, it is a bit challenging to recognize this kind of surfaces. So here's another example. Identify the surface parameterized by R U V is equal to 2 cos U plus V J plus 2 sine U K. Okay, and let's say U is between 0 and 2 pi, and V is, let's say, it doesn't matter. I just want, I don't know, 0 and 1, let's say. But it doesn't matter. We just want to know what is this? What is this actually? So we have x u v is equal to 2 cos u. Y u v is equal to v. And then we have z u v is equal to 2 sine u. Okay, so what does it mean here? It means that, hence, it means that x squared plus y squared is 2 cos u squared plus 2 sine u squared, which is equal to 4. Okay? So you need to understand what you're doing. So if x squared plus y squared is always 4, what does it mean? It means that when you cut this surface with the, if you look at the surface and you cut it off with a plane that is parallel to the plane, let me see. This is x squared plus y squared. Well, no, sorry. This is z squared. This one, we're adding this one. So it means that, let me just rectify this one here. It means that when you cut this surface off with the planes that are parallel to the plane xz. So let me do a graph here, much better. So this is x, this is y, and this is z. Okay. So what it means is when you cut it off with the planes, that are parallel to the plane xz, that's what it tells you here. It means that x squared plus z squared is 4. So it's kind of a circle here. Okay, so it's a circle, right? And this is true for all the planes you can use, right? So it's also true if you use another plane, and it's also true if you use another plane. You know, another way to see it is the projection on the xz plane is always a circle of radius 2, right? And now you have to look at y here. So for some y equal to some value v, the plane that goes through this y equal to v, right? This is v. The surface looks like a circle, and this is true for all the y's here, right? So if you gather this all information, it means that this is a cylinder. Okay? Here's the explanation. So the vertical section, since the vertical sections of the surface are circles, of radius 2, and y is equal to v, then it doesn't depend on, means that the surface is a circular cylinder. Well, I know that this might be a little bit hard, but the idea is this one. If I give you a parametric representation, there is no way you can know what is the surface. So what you do is you try to find what is the relations that are satisfied by the components. So you try to cut it off with planes and see how they look like, right? On the plane. So in this case, we use these planes, and for each one of them, it's a circle. Now we gather all of these circles, and because we are moving along the y direction, right? We are moving along the y direction, we add them up, like a circle, another circle, another circle, another circle. So this must be a cylinder, right? And of course, if the circle depended on the position of where you are, for example, if it wasn't constant here, if it wasn't 4, you couldn't say that. I mean, if it wasn't 4, for example, let's just say if it was, for example, 4v, like if it's x squared plus y squared, it's 4v, for example. What you would have is a circle, right? So I'm explaining here a little bit quickly. You would have, for some position v, you would have a circle of some circle. Let's say v is positive. You would have a circle. But then as you move along with the yz, you're going to have a bigger circle, right? So this is not a cylinder, right? You know, you have to work a little bit more to see if it's a cone or if it's a paraboloid cone, you know, because there will be like circles that are bigger, but you don't know if it's gonna be a curve here or it's gonna be just a cone. Like a cone is also the same thing, it's a circle, but you don't know if it's gonna be a curve or it's gonna be a line that joins all the circles, right? So in the case of a cylinder, they are all the same, and you know, that's sustainable. Sorry. Yeah, so that's the reasoning behind it. You need to do a little bit more. You need to do a bit more of this, so you can get acquainted with it. All right. So in this case, it's a cylinder. So let me take a break here, and we'll continue with these parametric surfaces. But don't worry, we're gonna guide you through this. We're gonna tell you what to do if it's too hard to identify the surface. So what is left is we're gonna talk a little bit more about some other examples, and then we're gonna speak about the surface areas, and that's it. And tomorrow we'll do surface and thickness. I'm moving a bit, yeah. Okay. Okay. Well, let me be back at 11:20. Okay. So welcome back. So when we have a surface, when a parametric surface RU V is given, there are two particular curves that lie on S. So these are the curves corresponding to the vertical lines and horizontal lines in the UV plane. Okay? Because you have the UV plane, and then you have the 3D plane. Okay? Now what RUV does is it takes a point and it gives you a point in R3. So if you take the line, if you take, for example, a line here, the corresponding curve will be when we fix, for example, here V equal to V0, and then you vary U, it'll give you a curve given by R, U, V0, because now we have only one variable that is left. And the same thing goes when you fix, for example, U. It'll give you another curve on the sphere. On the surface. So this is gonna be given by R. This is another curve that is given by R U0, but now V is variable, right? So these are, and there are many, I mean, there are many lines that you can draw like this, right? And you will have many other curves on the surface, right? So, but it's gonna be on the surface. That's very important. It's gonna be on the surface. So suppose this is the surface, but it's gonna be on the surface. Okay. Okay. So yeah, I think it's very important that we'll, yeah. Yeah. So, okay, just a quick example. If okay, then you can pretty much see that when you fix u equal to u0, we get xv is equal to u0 cubed, yv is equal to u0 sine v, and z v is equal to u0 cos v. So it's a circle on the, so this is a circle of radius u0, right? When we fix v equal to v0, we get xu is equal to u cubed, yv is equal to yu is equal to u sine v0, and zu is equal to u cos u0. Right. So and of course, now I'm gonna let you think a little bit about it, but here it'll be y, it'll be tangent u0 z. So this curve is something on the plane, y is equal to tangent u0z. So it's a curve. You don't necessarily need to draw it exactly, but it's a curve, right? It's a curve, right? You have the plane y equal, right? You have the plane here. You have the plane y equal to tangent u0. Because how do we know that it's on the plane? Because these two components, they satisfy this equation. So this is on the plane, right? And because x is gonna vary, because x is also varying, so it'll be something like that. It's a curve that is on the space. Now I do, just to let you know how it looks like, but this is a curve. This is a curve. Okay, so now let us do something that you're gonna be asked for in the quiz. We have seen that the surface, yeah. So this is what I was saying in the beginning. We have seen the surfaces are also represented by equations of the form fx, y, z is equal to 0, right? So in the following examples, we will go from the other side. So remember what we did. We started with a surface that is parametrized, and we converted this representation into an equation of x, y, and z. We did that with the cone. Remember, we did that with the cylinder, because this is an equation of a cylinder, circle on one. We did also that with the cone. Now you need to go back. How about going on the other direction? Like if I give you a surface that is given by an equation on x, y, z, following examples. Okay, now in the following examples, we're gonna go backward, which means that we'll start with a surface that is described with x, y, z, and then you will have to find a parametric. This is much harder than the other side. So, for example, find a parametric representation of the sphere okay? So, unfortunately, there is no systematic way I can give you to obtain a parametric representation of this. There is no way I can give you like an algorithm or something to do it. You have to do it case by case, and it depends on the cases. So for a sphere, for example, you'll have to use your knowledge. We'll use the knowledge about spherical coordinates to parameterize the sphere. So that's what we're gonna do here. So remember what was the idea of the spherical coordinates? So you have the sphere here, okay? Right? And we have the angle phi, and we have the angle theta, and we have the rho. But rho now fixed, which is equal to A. And now you have to move around using theta and phi. So these are the two variables that you can use to parameterize the surface. So any point, remember, rho was not fixed when we were doing triple integrals, because sometimes you have to cover the solid. But now we are on the surface, so it stays the same. Any point on the sphere has the form x theta x phi. Theta is a sine phi cos theta. Y phi theta is a sine phi sine theta, right? So this is x, this is y, and this is y, and this is z. Cos phi. Okay. And as you're gonna move phi, so of course you have to give the range of phi. Phi now, if you want to cover all the surface, you move from 0 to pi over 2, right? Because the way you do it is, for each phi, you go around, okay? For each phi, you go around with 2 pi, right? For each phi, your theta goes from 0 to 2 pi. And you do it from when it points exactly along the z-axis to the other direction, in which case you're just going to be describing only a point, right? Because when you rotate this one, it stays here, it's a 0, right? And the same thing happens here. And it's obvious if you plug in phi is equal to 0 or pi over 2, this one is equal to 1. And right, so if it's 0, if it's 0, then this is equal to 0, right? If phi is equal to 0, this is equal to 0, this is equal to 0, and this is equal to a, so it stays here. And same thing happens for pi. If you plug in pi here, it's here. So, but on the other, from between 0 and pi, it will give you circles. So you go around, you go like this, and then if you do it for this range of phi and pi and theta, it will give you the sphere. So this is a parametric representation of the sphere. Example 2. So as I said, there is really no one way you can do with this for all the surfaces. You'll have to use, it's a case by case. So for example, find a parametric description equation for the plane that contains zero, 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 and the vectors I minus j and j minus k, right? So here you're not going to use spherical coordinates. Here you're going to use your what you know about linear algebra. If you have a plane, right, and if I'm at the origin, if I have a point and I have two vectors that are on the plane, that is sufficient to determine all the plane. So this is the vector I minus j, and this is the vector j minus k, right? And this is the point 0, 0, 0. So every point on the plane can be reached. So any point on the plane, on this plane, has the form R U V is you take the point 0, 0, 0, and then you go along the direction of I minus j, and then you go somewhere along the direction of the other vector. So this is from linear algebra, right? So you must know that, right? So this is always the case. If I have two vectors and one point, this is the equation of the plane. And then that's it. You just add everything. It's u. So here, of course, it's it's u I plus u minus v j minus vk. So this is the equation. This is a parametric equation of the plane. So this is x uv, this is y uv, and this is z uv. Okay. So there is another example. Make sure you go and you read it on in my notes. I will upload them today. Okay. But the idea is always the same. You have to use your intuition, use something that you know, so that you can use an inequality, for example, cos square plus y square. But go and read the example and it'll give you an idea how to solve a couple of others. Okay. So the tangent plane. So if you have a surface, you want to know what is the tangent plane at some point. Okay. So suppose we have a surface with parametric representation R UV is equal to X UV I plus Y UV J plus Z UV K. Okay? And U is between A and B, and Y is between C and D. Okay? Okay, so consider the grid curve. Yeah, so this is a name that is, yeah, so these two curves that I gave you earlier today, like when you have lines on the UV plane, they're called grid curves. Curves obtained by fixing V is equal to V0. Then the tangent curve, then the tangent vector to this curve at the point P0 equal to R U0 V0, okay, is, make sure you understand the difference between the point U0 V0 and the point R of U0 V0. U0 V0 is in the UV plane, it's just the parameters. But the real point is the image of this U0 V0. So the tangent plane is RU. So you take the partial derivative with respect to U and you evaluate at the point U0 V0, right? So it's a del X del U. So this is the tangent curve at the point U0 V0. It's the point where yeah. Okay. So the diagram here shows. So if the surface looks like this, has this shape, and you have the two grid curves here, and this is the point where this is the point RU0 V0. So you have one tangent vector that goes like this, right? You have tangent that goes along this direction, and then the same thing will apply. This is the curve. This is the curve C1, and this is the curve C2, right? When you fix one variable. And then same thing will happen when you fix the other one. You will have another curve, and then another tangent vector here at the point RU0. Similarly, the vector RU0, no, RV is equal to del X del V U0 V0 I plus del Y del V U0 V0 J plus okay, so this is the tangent vector at R U0 V0 of the grid curve C2 obtained by fixing so here we're fixing V is equal to V0, and here we're fixing U is equal to U0. Now, the tangent plane at the point RU0 V0 is the plane that contains the vectors RU, RV, and the point RU0 V0. Or contains the point U0 V0 but normal with normal vector, or normal to the vector RU RV. Now why is this one is now we're gonna, I mean, this one will be much more easier because well, it depends on what you want. Like for example, if you want a parametric representation of the plane, this one will be useful. It contains RU, RV. If you want an algebraic one, we'll need normal. See, you must know that. If I give you a plane, I give you the normal vector. You must be aware of that. If I give you a plane, and I give you the normal vector, and I give you a point, then you can know, then the equation of the plane will be something, remember there's a formula for this. You have to write this as N1, N2, N3, and then this is a point X0, Y0, Z0, then the equation will be n1 x minus x0 plus n2 y minus y0 plus n3 c minus z0. Well, we're not going to prove this. It's we must know that, right? But this is an algebraic one, which is the one I was telling you, fxz is equal to 0. So if you want a parametric representation, you will need this one. You'll need the vector ru, and you'll need the vector rv, and you'll need the point xu0, v0, and you'll do what I did in the example. So let's, for example, let's suppose I'm asking you to find this one. Example. And remember that the normal vector does not need to be unitary. It doesn't mean to, it just need to be find a normal vector. Doesn't need to be no. You don't need to do the extra work to find a normal one, because anyway you're gonna divide by the same number here, right? By the norm of n, right? With the norm of n, with the norm of n, multiply by all of them, it's gonna be the same equation, right? It doesn't matter. Okay, so so I'm gonna give you an example of how to find a tangent vector of a surface, and then we'll talk about the surface area of a surface area of a surface, and then we need to talk about surface integrals. Okay. Okay. So let me give you this quick example. Consider the surface Okay, but I'm not gonna give you the range of UV. You can choose whatever you want. It's not that problematic. Let's say I don't know. I didn't really do it. I will have to do some, it would take me some time to figure out what's the UV here. But it needs to, so what is UV here? It's 1, yeah. Okay, so let's say U is between -2 and 2, and V is between -2 and 2. Well, this is a random thing. I just needed to contain U and V equal to 1. So find the tangent plane at the point. So here, be careful. Be very careful. Here at the point 113, it's the point itself. Then you have to find UV such that this give you 113. So here 113 corresponds to U equal to 1, V equal to 1. So we compute RU, it's del X del U, del X del Y del U, del Z del U. And if you do this, it'll give you 2U plus K. Now, if you compute RV, it'll be del X del V plus del Y del V This is V, not U. And it will be equal to 2V I plus 2K, okay? So, so for now you have to deal with this, because if you want to find the tangent vectors at the point 113, it corresponds to UV equal to 1. So it's equal to 2I plus K RV 1 is 2I plus 2K, okay? So now, if I ask you for, I need to find a normal vector. So a normal vector to this plane is given by the cross product right? It doesn't matter which order you're gonna take. So I'm gonna let you calculate this one, but here's a quick way if you wanna. I mean, of course, you can do it using the determinant, right? You can do it using the determinant, but here's another way to do it. Use the fact that it is associative, right? It is associative with the fact that the right-hand rule, like this is I, this is J, and this is K, right? And when you are like, a quick way to do this is use your hand, your right hand, and if your thumb points along the K direction, and you are rolling your hand from the direction along I to G, then it's going to give you K. So the result will always be given by the direction of your thumb. So if you take GK, it's gonna be I. If you take KI, it's gonna be J. If you take IK, it's gonna be minus J, right? It's always your thumb. It's gonna give you the direction. So that's a cool way to do it. So you can like, and when it's the same, when it's parallel, it's 0. So it's 0 plus 4IK plus 2KI plus 2K. Okay, so this is actually 2II. So as I was saying, this is 4. So IK, if you say, if you apply the rule I told you right now, it's minus J. If you do it for KI, it's J, right? It's, no, this is K, sorry, this is 2J here. I'm sorry. It's 2J. Oh, wait. Oh, it's 2J here, sorry. So, okay, we'll have to do it again. So it's 2I times J plus 2 plus 4I times K plus 2K times J plus 2KK. And this is equal to 4. Now, if you apply the rule IJ, you roll your 4 fingers from I to J, give you K, plus 4IK, give minus J, plus 2, now K, then that minus, now it's minus I. And now it's parallel, so it's 0. So if you do this, it's 4K minus 4j minus 2I. So this is the normal vector. So now I have the point. So the plane is given by the equation. Now it's 4. Now remember, this is not the right order, but it's minus 2I minus 4j plus 4k. So it's minus 2 x minus what is, so we are talking about this point here. So x minus 1 plus minus 4, y minus 1 plus 4, z minus 3 equal to 0. So now this is equal to x plus 2y minus 2z plus 3 equal to 0. Right? Because you take this normal vector with the point 1, 1, 3, and you apply the formula I told you here. N1, N2, N3, x0, y0, z0. You apply it here, and it gives you this. So, okay. And now I'll leave it as an exercise to obtain the parametric equation of this plane. But don't try to do it from the algebraic equation, and do it from RU and RV as I did in the example, previous example. So now we're left with the surface areas. This is also a formula that is only a formula you have to apply. And then after that, we're gonna talk about surface integral. We're gonna start talking about surface integral. And I think we should be okay, should be fine. I mean, we should be on time for this kind of, for this. Yeah, tomorrow. Okay, so we'll take a little break. We'll be back at 12:18. Okay. Okay, welcome back. Okay, let's talk about surface integrals. No, no surface integrals. Surface areas. Okay, so let S be a surface integral sorry. Let S be a surface parameterized by R U V is some function U V I plus Y U V J okay, and for now, let's suppose that with parameter domain, a rectangle V. So the parameter domain is where U and V are allowed to live. Say the example here, I have this rectangle, okay, and when I apply R, UV, this is a bit small. Okay, you have the surface. Surface S, and this is V. So what we do is we divide again, you know, the old idea of dividing these rectangles. So we divide this into small rectangles, call them R, I, J, and correspondingly, you're gonna have a little rectangle here. And this will be S, the corresponding rectangle. Not a rectangle, but the corresponding little surface, little chunk of surface will be called Sij, and call this point Bij. Okay, and this is the point Ui star. This is Uj star, some point. Okay, and this will be delta U, and this, we suppose that we're gonna divide them into similar, the width is similar, like the division is regular. So all these sub-rectangles, they have the same length and same height, same width and same, I don't know how it's called. Okay, so we divide these rectangles, divide them into small rectangles. Okay, so now if you wanna, what is this surface area? So the surface area of S is, you take all of these small, right, area, maybe it's better if I just take the area of this one. Then you're gonna sum. Okay, so this is the area of S. Okay, the area of S. Okay. Now, if you take a closer look at this Sij, okay? Take a closer look at Sij. This is something that looks like this. Okay. So I'm not going to give the whole details, but I'm going to tell you what is true. What is true? This is the point Pij, okay? You will have 2 second vectors, A, B, and you will have tangent vector, right? When you move along here, and you move along here, you will have R V at the point U star, V star, and here you will have the vector R U star. Okay, so these are really different vectors. Now the idea, as I said, I'm not gonna say the exact details, but the idea is when this is a very small patch on the surface, this will look like a rectangle, all right? Now AB will be very, very small, these two vectors. And because they're gonna be, now, here's two things. So first you're gonna approximate this surface with the rectangle, with the parallelogram that is spanned by A and B, right? It's gonna be a little bit closer to the area of this parallelogram here, right? When it's a very, very small patch. Now, in their turn, A and B, because they are very, very small, they can be approximated by, okay, let me write this. These two vectors, so so this is a bit conceptual. You will never be asked to prove this, but this is really for you to understand. So area, so when Sij is small, we have the area of Sij is approximately the area of parallelogram AB. This is my notation. It's spanned by AB. No, not, maybe not the real one. It's spanned by AB, which in turn, right? Now, okay, I will let you think about it. When Sij is small, okay, it's small, A is approximately given by R U star times delta U. And this is really the definition of a tangent vector. You take this point minus this point and you divide by the amount of the increment on U, delta U. So when this is very small, it's when delta U is very, very small, it's close to the limit. And our U star is actually the limit. So it's really nothing new here. And B is approximately given by delta V RU star V. So what is the area of this one, which is actually equal to, so the area of this one, so the area of this one is, you remember this formula? So if the area of Sij is approximated, so if A and B are approximated, so the conclusion of all of this is the area of Sij is approximately given by the determinant of the norm of the vector delta U RU star U star delta V. This is cross product with RV, right? And these are scalars, so I can take them out, which is delta U and they are positive. Okay, so the area of S is actually equal to the sum, approximately equal to the sum from I to N, from J. What did I use here? NM. M times delta U delta V. Okay, so when N M goes to infinity, this becomes an integral. This is a function. This is a function. So it's evaluated at the point U star V star, but it's also a function, right? It becomes an integral. Now this is a function. Okay, so this is a function of U and V, right? Now this one becomes the A, and then this one becomes the rectangle B. So this is the double integral, you know, we've been talking about like the last couple of weeks. So this is the reasoning behind it. So where okay. So the only problem with these integrals of surface integrals, and that's the downside of it, is it's really long. It's really long and hard to compute. And there are very few cases where you really can get something that you can compute as a double integral. Because remember, you have to take the cross product, take the norm. That this is, I mean, computationally speaking, it's a very demanding computation, because you have to take the derivative of each direction, take the cross product, and the cross product is not a, it's a really, it demands a lot of. I mean, if you use a computer, it'll use a lot of the memoir of the computer. If you want to use you want to compute the cross product. So if you want to use, so you're gonna compute the cross product, then take the norm, which is also a lot of square root, and you have to take square root of something square, right? And then the integral itself is not guaranteed that you can be done. It's really, there are a few cases where it can be done. So in a lot of cases, we'll use a computer to do this. But in some cases, some magic can happen and a lot of simplifications. So for example, in the case of a sphere, a lot of magic will happen because of the cos and sine identities. So I'll give you the example of the sphere, and I think there are other cases where it's easy also. I mean, I think a torus also is easy, but that's the problem list. So I'll give you the sphere, and the problem list you'll be asked to first find the parameterization of a torus, right, a donut, and then find the sphere, the area of a donut using this formula here. But the composition is exactly the same. You need to find, well, use this example if you want to compute, but you'll have to use your own parameterization, right? So make sure you have the right one. So let's make an example. Okay, so a sphere, we already know what is a. Okay, so there are two cases. I mean, if you want to compute the surface of a sphere, you have the possibility of taking the z is equal to square root of, x squared plus y squared, like minus 1, plus a squared. It is minus, and then take the formula we gave you in the beginning, right? Remember the dz, that was also a formula for the area of a surface, but the surface has to be given by a graph of a function. You can also do that and then multiply by 2 because it's the same area on both sides. But here is another way to do it, using the parameterization of the whole sphere. So we're gonna use so consider the sphere. You see, we got our parameterization of the sphere earlier. So consider the sphere x is equal to a sine phi cos theta, y is equal to a sine phi sine theta, z is equal to a cos phi. So, and now phi is between 0 and pi, and theta is between 0 and 2 pi. All right? So this is already given. If I have a parameterization of a sphere, you got this. Now you have to compute. So what is r phi? It's a, right? So it's a cos phi cos theta I plus a cos phi sine theta j minus a sine phi k. Now r theta is equal to minus a sine phi sine theta I plus a sine phi cos theta j 0. Okay. Now again, you can use the trick I gave you earlier, like associativity, the associativity of the cross product, or you can do it by hand, right? What is this? So you have to, first of all, you have to compute this, right? Determinant of I, j, k del x. Okay, I'm not gonna write it down here, del x del phi, because it's gonna be really long. Del y, but this is what we done here. This is del x del phi, del z del phi, right? This is del y del phi, and this is del z del phi. And the same thing goes for theta. And this is del x del theta, del y del theta, del z del theta. All right? Okay, now you compute. It'll give you this. A squared sine squared 5 cos theta I plus a squared plus sine squared 5 sine theta j plus a squared sine 5 cos 5 k, right? So it's really nothing. You just have to multiply. Like, see, for example, this is del z del theta, and this is del z del, this is del x del theta. See, so if you multiply, this is gonna give you 0, and del z del phi with this one. So if you multiply this with this, it's gonna give you a squared sine phi squared del z phi. Yeah, this one. This is del y del theta. So you multiply this by this. This is correspond to this line, and this one will be 0 because del z del phi is 0. So you multiply, it will be I don't know. It's a yeah. So just do the calculation. It'll give you this. Okay. But why is it that? And then del for k del x del phi. Yeah, it will sine phi. Yeah. So yeah, for this one, for example, you'll need to use the identity cos square plus sine square is equal to 1. Yeah. Okay, so just make sure that the calculation is okay. So as I told you, this is a very long, and then you'll have to take the square root of that. You have to take it to the power 2 and then take the square of it. Anyway, if it's plus or minus, it doesn't matter here. It's gonna be square. The only thing we care about is this. This is the norm. So it's square root of a to the power 4 sine 4 phi cos theta square plus a4 sine 4 phi sine square theta plus a4 sine square phi cos square phi. Now you can use the fact that these two are the same. So this is a4 sine 4 phi plus a to the power 4 sine square phi cos square phi. Now again, some magic will happen here, as I said, because this is A4 sine 4 sine to the sine square phi sine square phi plus A4 sine square phi cos square phi. Now again, you use the identity, which will give A4 sine square phi. Now this is A squared, and this is sine phi, because sine phi is always positive, right? Remember, phi is between 0 and pi. Okay, so all this is just this quantity here is simple. So the area of the sphere is A is the integral now the domain. Now the domain is where phi and theta are allowed to vary. So it's from 0 to pi, 0 to 2 pi, A squared sine phi d phi d theta, and this is A squared 2 pi, and this is minus cos phi between pi and 0, which is 2, right? All right, so this is the area of a sphere, 4pi a squared, the usual formula, you know, and we didn't have to multiply by 2 or use any z or square root of anything. But of course, there's this calculation we had to make, and there's, as I said, there is no guarantee that in other parametric surfaces it's gonna be as easy as this one. Sometimes you're gonna get an integral that you cannot do. Okay, so any questions so far? Yeah. So if there is no question, that's it for the area. So we're done with the area of the surface. Now, the surface integral, the beginning will look really like an area. It's really easy. So maybe I'm gonna start. Maybe I'm gonna take the 5 minutes now to give it. Now, the only thing is, it's gonna be a little bit confusing when it's gonna be another type of surface integrals, right? There are two types of surface integrals. There is the one that we're going to introduce right now, which is easy. It's really the same one as an area of a surface. The only difference is there will be another type of surface areas, which are a bit confusing. And yes. Yeah, so maybe tomorrow we're going to do this. So let me start with, let me take 5 minutes to introduce this. Surface integrals. Okay. So again, suppose we are given a parametric representation of a surface S. Okay, and UV are in some domain D. Okay, we first suppose, so we're gonna suppose it's a rectangle, but of course the same thing applies if it's not a rectangle. You just have to apply what you know about integrate and about general domains in the 2D case. So here, it's really nothing new. I mean, we're gonna suppose there's a rectangle and we divide it just as we did. And we divide it, you're gonna see the difference. There's only a small difference. And we divide it and we divide it into subrectangles. Okay? Suppose that f, now here is it. We're gonna introduce a function, f x y is defined as a function on our tree. Okay? Then what we'll do is remember what we had. We had the surface area, we had the surface, right? And then we divide it into very small sub patches on the surface, right? We call them Sij. Now we are on R3. So here what we will do is we take the point here, which is the point Pij. So instead of just taking the area, what we will do is we're going to introduce a function of xi and we form the Riemann series Riemann sum you take the function f and you evaluate, so this is the point P star. You evaluate f at the point Pij star, you multiply by the area of, right, delta I'm using a bit, yeah, so be careful before I use A of ace. Yeah, so be careful. Here I used the area here, right? When I was explaining this, I used the area of this. And here I'm using another notation. So just make sure you're following me. So this is the area of the patch. So we form this kind of surface, this sum. So we have seen that this one, the surface of this little surface is approximately given by the scalar product, the dot product RU, RV, evaluated at the point Pij times delta U, delta V. Okay? So when we take the limit, and infinity as before, we get the integral of R U R V times, okay, let me write it the other way. We get the integral of the function f evaluated at the point R U V times the scalar R U R V dA on the region D. Okay, so this is, you might think, why are we complicating our lives? Why do we need this kind of integrals? Like, okay, surface area, we care about surface areas. We'd like to know how much tissue it's gonna take me to cover a sphere, or how much tissue it's gonna take me to cover a kind of shape of a surface. But why do we care about this in the real life? Why do you want to form this complicated thing? Well, it's also, I mean, the main application of this surface integrals is in physics and all that. In this class, it will be the mass, as we did. So if you have been following the class since the beginning, here is what we have been doing. We started with a surface on the plane, right? A lamina, right? And we gave you rho of a function fy, and we told you what is the total mass of that. You needed an integral of the form rho xy dA over d. Then what we did is we went to a wire, right? We gave you a function rho fxy, but now it's a wire, and we told you what is the mass of this wire. Then we need an integral of the form rho, now evaluated at the surface. Now it's a curve, ds, but rho xy is evaluated on the curve. Then we gave you a solid, right? A solid ball, for example, right? Now we have a function rho xyz, and we told you what is the mass of this one. Then you needed a triple integral over the solid S, rho xy z dv, right? Now this is a plane one, okay? Well, the last one, I think, for this class will be, I give you a solid, a sphere, I give you a surface, and I give you a density function rho xyz, and I tell you what is the mass of this shell. Now you need a surface integral. You will need the surface of the form rho xyz, but evaluated at the surface. Now you will need ds. But here, be careful. This is little ds, and this is capital S. Okay? And then you have to find the parameterization, right? Rho evaluated at UV, and here it's the domain D. Okay, right? So this is the main application of this kind of surfaces, this kind. So if you have a surface and you have a mass, you have the density, then what is the mass of this little patch? It's just rho evaluated at the random point there times the area of this really small area, and then you take the sum over all this, the surface, and it will give you the mass. So make sure you understand how to do this kind of computations and which one you choose. Okay, so yeah, make sure they will be tested on that. So if you have been following the quizzes, I was the one making the quiz for. Well, there was an error for this one, so we gave you 3 points, but we wanted you to do it. So I made the error. I forgot the square root of 2, but it's okay. So make sure, like we have been doing this in all the quizzes, right? Make sure you understand how to do this in this case. Okay, so next time I'm gonna give you an example of not necessarily a mass, but it's the same thing. It's like once I give you rho, it's whatever the function here, you're gonna just compute it. Okay, so tomorrow I'm gonna give you an example of this, and we'll start talking about other types of surface integrals. All right, I was wondering if you would like to give me some suggestions regarding my copy in physics, precision in physics. Okay, all right, so this is a private. Okay, so thank you so much, everyone. I'll see you tomorrow. Yeah. Okay. Bye-bye.